We haven't touched code for a few videos, so it's probably time to get back, but I do feel it was necessary to get that foundation of the matrices and how they can perform linear transformations and move vectors around and that sort of thing. Now it's time to write some code. I want to do something interesting. We just spent a lot of time understanding rotation and why rotation works. I want to use those concepts to get our ship, our little ship that shows up in our game. I want it to rotate, so we're going to use the matrix class to do that. We need to define a function. Let's say inline. We'll return a matrix 2D, and I'm going to say it's rotate, float, angle, but I'm going to be explicit and say angle in radians. I'm not sure what English history happened to give us degrees and why we cut circles up into 360 degrees. I like to think in radians. That's a natural way of thinking of circles. I know that's probably not the way you grew up with. Try work as hard as you can so that thinking in radians is second nature, because it works so much more elegantly than trying to deal with the 360 degrees. I also feel the same is true for working in metric units versus the English units. The English units are nice, it's culturally, yeah, we were raised in it and it kind of works, but I think some lengths were based off some dude's arm or hand or who knows what, and the metrics unit is just so consistent and it's nice. And I remember taking my physics classes and working in metric and thinking, wow, this is so much more elegant than what I was raised with. And now I'm on a soapbox and I'm just pontificating. Let me get off my soapbox. I'm going to be explicit here and say radians. I think that adds a lot of value. I don't think I've ever worked in a math library that has said radians. It just says angle, and then I have to Google the API and see is it degrees, is it radians, how do I need to convert between the two, so on and so forth. So I'm going to say angle in radians. Alright, and I'm going to make it a member function. I'm actually going to say this is going to be static. Alright, so we will call this rotate function by scoping into the matrix 2D class. The reason I could make this a non-member if I want to, but I really think this is very specific to the matrix class, so I'm going to add it to the matrix class, or struct, I guess. The reason I'm using struct is I just want everything to default public, and it's struct this is almost a primitive type, but not really, and so on. I think I've pontificated about that before, but anyway, this is going to be a factory function which will create a matrix 2D that will rotate any vector it's applied to by this angle in radians. And so a factory, if you think of a factory is a design pattern. If you go look at the Gang of Four or just Google factory design pattern, you'll find plenty on the subject. But very simple concept. It's a function that creates, it's almost like a constructor in a way, but it creates an object. And I guess I could make this into a constructor if I wanted to, but we're going to do something a little more trickier than what I think a constructor should do. So I'm going to make this into a factory function. Factories in real life, you feed them a bunch of material and out pops a product. So car manufacturing, for example, give it a bunch of steel and plastic and whatever else they require, and out pops a car. And we're going to feed this factory function in angle and radians, and it will pop out a matrix that I can apply to a vector that will perform that rotation. Let's go implement this. Let's matrix 2d.inl, and just for consistency, I think I'm going to place it right here between the constructor and the operator. Remember, the operator is a non-member operator right here, and the constructor is a member. And so I've tried to organize this code such that here's the constructor, here's some helper functions. So we'll try to be consistent in our implementation file as well. I no longer need to say inline nor static. I declared the function as inline and static right here. Rotate angle and radians. I do need to add scope though, like so. And then I'm going to return a matrix 2D, and I could implement this right here, but not quite ready for that because we want to use test-driven development and implement the tests first. So consistent with the other files is I try to be as consistent as possible. You can't always be consistent, but I'm going to write the test between the constructor and testing the operator. This is going to test matrix 2D, and we're going to test rotation. Okay, so matrix 2D op, I would like to say operator, but that's a keyword. So op the operator matrix. Gets matrix 2D, rotate, and we'll start out with 0. And then we're going to say expect float equals op dot row 0, column 0. Let's just do that for now. Oops. Save, Control L, Control V, 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 because I need to do all 4 values. Row 0, column 0, row 0, column 1, row 1, row 1, column 0, column 1, like so. And then we'll work out these values out here. So to be consistent, let's do op like that. And now I can copy this. And I want to do just a few test cases so I can feel good about that. So paste, paste, paste. If copy and paste makes you feel uncomfortable as a programmer, that probably means you have come of age in your programming. You've met a milestone, so to say. You've gone from white belt to yellow belt, or whatever the next belt is in karate. Copy and paste should be one of the first things you realize is generally not good, but I think here we're okay. And it's okay to break the rules as long as you understand how to follow them. That was something I learned in English, and I like that saying. Okay. Let's see if we're all good. Okay, so rotate by 0, rotate by, I want to say pi, but I don't have a pi. I'm going to pretend like I have a pi for now. Let's do pi over 2, and let's do pi over 4, and I'm actually, let's beef this up a little bit. It's probably not necessary, but I'm going to try. Let's do a negative pi over 4. And just for tickles, let's do pi over 3. Oops. And then negative pi over 3. Now I could write a for loop that does all this stuff and maybe calculates it and so on and so forth. But with the unit testing, I kind of like to hard code some values in here. I think it helps with readability just to see, oh yeah, that's working. And then I could write a loop. I think we did that with the vector class. We hard coded some values, and then I wrote a loop to try a bunch of other different operations. But okay, so let's do some mental exercises here. If I have a coordinate system and I have a vector, I start out with the unit vector 1 in this direction, and I rotate it by 0. Well, what should that give me? Well, the rotation matrix, if I recall, the rotation matrix from the previous videos is going to be cosine theta, negative sine theta, and actually well, I should have probably written this sine theta first, because mentally I like to think of it as this is the one basis vector, this is the next basis vector. But either way, cosine, negative sine, sine, and then this is going to be cosine again. Alright, the cosine, now we're doing rotation of 0. Well, cosine of 0 is 1, and I can just memorize that from my trigonometry class. But if you think about it, again, we're dealing with those triangles. I'm going to kind of draw a triangle right above this guy. And remember I said cosine is here's theta, right? And cosine is this adjacent side here, and sine is the opposite side. Well, what is the length of this adjacent? Oh, it's 1. Go figure. It's a unit length vector. It's 1. So you can think of it that way as well. Cosine of theta, well, it's 1. We haven't rotated our unit length vector anywhere. And then the sine, well, we're not going up and down. That's an arrow, by the way. That doesn't look like an arrow, but we're not going up and down at all. We're at 0 on the y, so sine will be 0 as well. So let's type this in here. Row 0, column 0 will be 0. Row 0, column 1 will be, or no, that's going to be 1, sorry. Row 0, column 1 will be negative 0, but negative 0 is really the same thing as saying 0, so I'm going to say 0 there. Row 1, column 1, well, that's going to be 0 still, and or row 1, column 0 is going to be 0, and row 1, column 1 will be 1. Okay, so rotation by an angle of 0, that was pretty easy. Let's do a rotation of pi. Well, rotation of pi, let me get rid of this. I think we're done with that. Rotation of pi means we're going to take this unit vector we started out with on the x-axis, and we're going to rotate it by pi, which will bring it right here. Well, what is the cosine of that angle? What is the length of this side? Well, now we're going negative x there. So if you think of our triangle again, it's a triangle. Let's bring the triangle up. I can draw the triangle again. Here's the triangle. All right, well, the length of that side, this adjacent side, if you would, well, that's negative 1. Right? And then what's the sine? Well, the sine went back to 0. We're still stuck on the x-axis. So maybe not as interesting as it could be, but cosine's gone to negative 1. So negative 1, 0, 0, and negative 1. Oops, negative 1. Okay, good. Pi over 2. And let's start out with a new axis coordinate system. I wish there was a better way of erasing bigger stuff. I guess I could have made my eraser bigger, but whatever. Coordinate system again. Here's our original vector that we're going to rotate. And the rotation of pi over 2 will be up this way. So that will bring our vector like this. Well, what is the cosine of that? Well, cosine, we're not going anywhere in the x direction. Our adjacent is 0. Okay, so cosine goes to 0. But sine, well, now we're going up in the 1 there. We're now, instead of going 1 this direction, we're going 1 this direction. So that's the sine of theta is 1. So that should come out quite nice. Pi over 2, we're going to say cosine is 0. Sine, but it's negative sine right here. Negative sine is going to be negative 1, and then we'll have a 1 because sine theta is 1, and then again we have another cosine theta, that's going to be 0. Good. Alright. So, sorry, this testing video, I noticed we're already at 12 minutes, and again, you can always skip the testing videos if you like, but I think they're important, and they will get a little long, because testing can get long. That's the trade-offs with testing, but then again, I like this stuff backing me up, especially when I start changing my code. Okay, pi over 4. Pi over 4, let me get rid of that there, and black. Pi over 4 means we're going to bring this vector to right about there. Well, what's the length of this side and what's the length of this side? If you remember from the previous videos, it's going to be root 2 over 2, and the same thing as a 45-degree angle. Ooh, I just said 45 degrees instead of pi over 4 radians, but root 2 over 2, root 2 over 2. Well, what is root 2 over 2? It's roughly equal to 0.7, but I want to be more precise than that, so let's ask Google again and get a more precise number, not a perfect number, but a more precise number. A precise number is root 2 over 2, but I can't really, the computers, the best I got to do is actually get a floating point value, 0.7, whatever the digits are after it. So let's ask Google what's the best we can do. I'll bring this back up here, and I'm going to say square root of 2 over 2. Oh, it looks like lots of other people, and including me, have searched for this. What are the values? See, that's more precise. It's not perfect, but it's better than saying just 0.7. So let me copy this. So Control C, go back over here, and see they're all going to be positive. So let's just dump them there, like so. And that's kind of, that's a lot of magic numbers, isn't it? I could make that a constant if I want to, but yeah. How about, I don't know. I could say const float square root 2 over 2 gets that. I don't know if that's going to help readability. I'm going to do alt drag here and just type that. Actually, I can do a copy. Last time I tried this, I think this worked. Copy that, and then alt drag over that, and Control V. Yep, sounds good. Okay, so I think we're good. Now, negative pi over 4. Well, how's that going to change things? It's going to be very similar to what we just had. Maybe it's good I made that constant because we're going to use it again down here. So let me just clean that up. And we'll go black. Get that back out there. Okay, negative pi over 4 here's our original vector, and then we're going to rotate it this direction. So there's our theta right there. So what's the length? I get a different color. What's the length of this side? What's the length of this side? Well, we're still positive x here. Alright, so, and that's cosine. So it's still going to be square root 2 over 2. But now we're negative. On the y, we're negative, which is our sine. That's our opposite side from this angle theta here, our sine. So our sine goes negative, and our cosine stays the same. So let's just put that in there. Square root 2 over 2 for the cosines. That's true. And then the sines, well, it's going to be, the sine theta is now negative square root 2 over 2, but then we got a negative of a negative. Right? So it's kind of like negative of an, well, that's a minus minus operator, but it's kind of like a negative of square root over 2 over 2. Well, I can just say square root 2 over 2. But then this sine theta, well, this is sine theta is negative square root 2 over 2, so I have to keep my negative there. I don't have the negative cancel out the negative. Okay, and then pi over 3. Pi over 3. Let's clear this out and start over. Pi over 3, that's a common angle as well. In fact, if we hit Google here, let me hit Google. I'm going to bring that chart back up I had in the previous video. So here we go. Bring this up here. So pi over 3 is right here. So the sine is root 3 over 2, and the cosine is 1/2. Well, 1/2 I can represent that in decimal perfectly, but root 3 over 2 I can't represent perfectly. Let's go here, square root 3 over 2. So that's going to be our square root 3 over 2 number. Let's make a constant for that and be consistent with the rest of our testing. Square root 3 over 2 is equal to this number. Put that there. And I think the compiler is going to complain actually, because we're not suffixing these with f to make these literals float, so then they're doubles. But let's see, maybe the compiler will complain, maybe not. We'll just roll with it for now and add them if we have to. Square root 3 over 2, so let's bring this chart back up. Square root 3 over 2, that's our sine. Alright, so rotate pi over 3, well, that's going to be, here's our original again, and then pi over 3 is, we're doing thirds now instead of fourths, so that's actually going to rotate this vector up like that. Okay, and then here's our theta, and here's the length of that side, and like that. Okay, so that's why the sine, if you notice, sine is root 3 over 2, but the cosine is 0.5, so maybe I should have put this right in the middle there instead of as far over as I did. But hopefully you get the idea. Root 3 over 2 is greater than 0.5, so we have a longer side here and a shorter side here. Okay. A lot of math. Okay, so row 0, column 0, cosine is going to be 0.5. Negative sign will be negative square root 3 over 2. And then this sign is going to be square root 3 over 2. And then this will be 0.5 as well. Okay, last one. Same thing but negative. I'm going to draw this out just because I think it's good to draw this out, even though it takes time. I hope it helps you. If you've stuck with me this long through the unit testing video, then I definitely hope this helps you to see this. We're going to, here's our original vector. Again, it's still length 1, but I'm gonna zoom in, if you would. Let's give ourselves some room. And then we know we're going to go to 0.5, and I'm going to change color just because I can see we're about to collide with this matrix here. But 0.5, and then it's root 3 over 2 will give us something similar to this. There we go, and I said I was going to change color, and then I didn't stick with it. Something like this. And then here's the length of the opposite side. Here's our theta. And then here's the length of this side. So we know the cosine is 0.5. And the sine, this opposite side, is going to be root 3 over 2. So, but it's negative, isn't it? We're going down now on the y. It's negative root 3 over 2. So here we go. Cosine's 0.5, so I'm just going to put 0.5s in for the cosines, make that easy. And then again, we have the negative of the negative, so negative of square root 3 over 2. And then this is going to be negative square root 3 over 2. Well, again, negative is just a positive, so I think we're good there. Whew, a lot of derivations to get all those unit tests, but I think that's a good mental exercise. Let's control F5. Hopefully this fails miserably. Well, it might not even build. Pi. Oh yeah. We don't have a pi. I'm gonna stop the video here and move on to the next one. Go get a lunch or take a break or something, and come back and let this seep. Maybe even let this seep overnight, and then come back and watch the next video tomorrow. Give your brain a little bit of time to process this and think about it offline. Go do something that's mind-numbing, that your brain can just flow and kind of mindlessly think about this stuff. That's good for your mental growth, so to say. I definitely believe that sleep between concepts helps, instead of trying to drill something for hours and hours and hours on end. Okay, I've rambled enough. 22 minutes. Next video.